Let me start with introducing the speaker. Today we have the pleasure of having here Huyen Pham, and I will keep the introduction short. Huyen is a very well-known researcher in the area of financial mathematics and stochastic analysis. His position is currently a professor at Paris 7, or also called Paris Diderot, and in the laboratory of probability statistics and modeling. And yeah, he has a number of editorial positions, including being editor of Applied Mathematics and Optimization, and also is one of the associate editor of Finance and Stochastics, so one of the premier journal of our field. And yeah, as I mentioned, he has been doing a lot of work over the years about stochastic differential equation, partial differential equations, its applications to finance, like stochastic control. Most recently, he got interested in machine learning and has been doing a lot of exciting work on using machine learning for solving partial differential equations, which I think is the topic of today's talk. So without further say, Huyen, the floor is yours.
Okay, so thank you. Okay, thank you, Agostino, for the nice introduction, and thanks to all the organizers for giving me the opportunity to give a talk in this webinar. So today, my talk will be based on joint current work or work in progress with several people. So some colleagues, Xavier Varin, Mathieu Laurière, and some PhD students, so Maximilien Germain and William Lefebvre. So the topic is it's about in fact a deep learning method, as you can see from the title, for solving a class of symmetric problems. So I will precise later what I mean by a symmetric problem. And using, in fact, a new class of networks that have been recently introduced in the literature, so namely DeepSet and DeepOnet. So to introduce the topic, let me first recall, okay, well, so in a nutshell, there's some basic principle of deep learning method for solving, I mean, PDE problem or control problem. So in this framework, so usually you have some functions, so from some input space to some output space, so which is a solution to some problems, or some PDEs or optimization problems. So it's typically an option price. Okay, a solution to some PDE or some value function, okay, from coming from a stochastic control problem. And you are often interested by also computing not only the function as a solution, but also its gradients, okay, because it gives you access typically to the hedging strategy or the feedback policy. Okay, and then you consider some class of approximators, okay, and so probably the most popular one are deep neural network, okay. So here is the classical architecture. So it's very popular. So even if it is now subject to some criticism, because maybe due to its lack of interpretability, and maybe because it's a very highly parametric class of function, maybe too much flexible, so it's sometimes hard to give some interpretation. But anyway, it has already shown a lot of spectacular success. And then once you consider your class of neural network, your architecture. Okay, so the next step is to train this neural network. So in order to learn the function that you want to approximate, and so this means that you have to minimize some loss function. Okay, so in other words, optimize over the parameter of your neural network. So with some loss, which should be related to the objective or the criterion of your problem. And so this is performed by simulation, okay, so which represent here your data, your input data, okay, and by typically a stochastic gradient method or its a variance, okay, with a similar change which usually is related to the structure of your model that you want to solve. Okay, so now there is by now an extensive literature, okay, on this topic, so with different algorithms, which in fact essentially differ according to the choice of the loss function, so which can be global, so in the sense that okay, you have your problem, okay, you just solve in a brute force, or I would say local, okay, so inspired by a dynamic based methods. Then you have okay to choose how you simulate your training data. So it's and of course it's an important issue because it's related to how you will explore or exploit your state space. And in fact, this choice is okay is depend on the approach that you adopt. So it's a deterministic or probabilistic approach. Okay, so the same distinction that you have in a classical numerical method between finite difference and Monte Carlo methods. Okay, and so now what could be the next challenge in this area? So in fact, most of the existing works in these topics, okay, so focus on the resolution of PD or control, okay, typically when the input space is of finite dimension, okay, so vector, and often when for a given model. So okay, so you have some coefficients, a model, which means that if you want to change the coefficient, the model, so the terminal conditions, the drift, the volatility, usually in fact you need to re-implement another algorithm. You need probably to change your loss function, and then of course it's maybe costly to re-implement again your algorithm. Okay, and so our aim here is to go further, okay, by considering an infinite dimensional problem, so which can be of different nature. So either because the input is of infinite dimension, okay, so the application we have in mind is typically coming from a mean field problem, where here you have some PD which is defined on the Wasserstein space of probability measure, or the infinite dimensional nature may come from the fact that you want to solve the problem, okay, for not only for a fixed model but for a family of model, possibly non-parametric. Okay, so it means that okay, you want to solve for different drift, different volatility coefficient, different payoff. Okay, and of course it's important regarding the question of robust methods, because usually you may wrongly estimate your coefficient. So okay, so if you want to have another coefficient, okay, you want to obtain quickly the solution to your problem. And it turns out that in fact it is now possible to address such issue by taking advantage, in fact, of recent advances that have been made in the machine learning community, okay, with the introduction of new neural networks. Okay, so in particular here in this talk, I will focus on the case of DeepSet and their derivative network, okay, which has been designed, okay, to deal with data defined on set, which possess some symmetric feature both on the input side and output side. Okay, and another new network is the so-called DeepOnet, which in fact has been designed in fact to learn not only functions but in fact operators, which means that you want to learn operator, meaning okay, you want to learn of a function, an operator defined from a space of function to another space of function. Okay, so let me also mention the recent say alternative to DeepOnet, which is called a Fourier neural network. But in this talk, I will mainly focus on DeepOnet. Okay, and so so the outline of this talk, okay, will report some of my recent work on this topic. So and so it will be divided in two parts. Okay, so in the first part, which is the main part of this talk, okay, I will consider okay, mean field PDE. Okay, and the second part, okay, which are still a work in progress, okay, will be concerned with some robust portfolio optimization problem using DeepOnet and DeepSet. Okay, so let me now talk about the first part. Okay, so let me introduce this this second order mean field PD. So it's a PD defined on the Wasserstein space. Okay, so which means that the argument now is mu. So it's on the Wasserstein space of square incredible probability measure. And so this PD, okay, involve okay, derivative with respect to the measures. Okay, so the red part here. So you have okay, derivative with respect to mu. Okay, so in here it's the notion of derivatives that we use. Okay, is the L derivative for lifted or Lyon's derivative. So we'll not go into the detail of this derivative. So the only thing that you need to know for this talk, okay, is only the fact that okay, if you look at the derivative taken at some point, so it is a function, okay, defined from Rd into Rd. And so as a function, then you can define, okay, its cross derivative. So if you view as a function of x, okay, so it is now a function from Rd into Rd times d. And you can also define, okay, if you view as a function of mu, you can take its second order derivative. Okay, so the partial second order partial differential with respect to mu. Okay, and then okay, we take an Hamiltonian H, okay, which has a expectation or integral form, okay, in this way. Okay, so it's an integral of the first integral is respect to the measure mu, and so the second integral, okay, is a double integral, okay, respect to also mu. Okay, so of course, so what is the motivation for considering such kind of PD? So as you already guessed, so the main motivation comes from model of large population of interacting agents, so which can be either in a strategic interaction or in cooperative interactions, leading either to the theory of mean field game or mean field or Mark inverse of control problem. And so this PD, in fact, so correspond to MFG or MKV, correspond in fact to the asymptotic regime when the number of agents goes to infinity. So let me here just point out that here we consider a PD where it's really a second order PD in the sense that it involves, okay, the second order derivative with respect to mu, okay, and in fact it is related to the fact that we also allow here the possibility of common noise. Okay, so by now there is a huge literature on these topics. Okay, and so I will only quote the main reference. Okay, the book by René and François Delahue. And in particular, the PD of the previous slide, so which is called a master equation in mean field game or Bellman equation in a Mark inverse of control problem. So it has been extensively studied over the last year, mostly from a theoretical point of view. So either in the PD community or in the probabilistic community. So I quote here some people who are involved in this exciting topic. And so here, our main goal here is rather to it's a numerical purpose. So the aim is to find a solution to numerical approximation to this PD. Okay, of course, such kind of problem has been already investigated, and I mentioned some papers by René Carmona, Mathieu Laurière, Jean-Pierre Fouque, and also Lars Rutoto and Stanley Oshers. Okay, but here, okay, we use a different approach, and so let me describe our methodology. So the first step, okay, would be, of course, to reduce this infinite dimensional problem into a finite dimensional problem. And so this is achieved formally as follow. So the basic idea is simply to look at the PDE. Okay, so you have a PDE on the Wasserstein space, and you restrict on empirical measures, okay, supported by endpoints. Okay, and then you look at the solution to the PDE. Okay, restricted at empirical measures. So it can be in this case viewed as a function of the supporting point of this measure. Okay, and by using the connection, the derivative connection between a function viewed as a function of on Rd power n or as a function of the evaluated as an empirical measure. Okay, so using these derivative relations. Okay, then plugging at least formally this derivative connection into the PDE, and neglecting the term of order 1 over n. Okay, you obtain formally, okay, such kind of PDE. Okay, which is written here. So it's now you have a 5-dimensional PDE. Okay, in Rd power n, and of course you want to ensure that such PDE give you a good approximation to your original PDE in the Wasserstein space. And in fact, there is a recent paper by Gangbo, Mallorca, and Switch, who proved by PD method, in fact by viscosity solution method, that indeed the solution to this 5-dimensional PDE converge, okay, to the original solution to the PDE in the Wasserstein space. And so here, alternatively, we shall adopt a probabilistic approach, which is also useful to design then the algorithm, and show not only the convergence, but also the rate of convergence for Vns, but also for its gradient. Okay, and so as in the paper by Gangbo and Mallorca-Zwich, we were only able to deal with the semi-linear case, which by semi-linear case I mean the case when the dependence on the second order derivative is a linear. Okay, and so in the semi-linear case, okay, which means that okay, you have it's a linear respect to the second order derivative. Okay, with Hamiltonian in this form, then okay, you after some simplification, okay, your PD, okay, is reduced into this form. Okay, so in other words, okay, you have some linear part, okay, some linear part of the PD, okay, where I introduce okay, an auxiliary coefficient B, okay, that of course I subtract to the semi-linear part here, okay, with this coefficient B. Okay, so why do we introduce such B? So in theory, B okay, can be just taken to be 0. But in practice, this coefficient B, okay, which will represent in a drift coefficient, will be crucial, okay, because it will okay, correspond to the drift of a training simulation, and it should be chosen, okay, in to explore well the state space if you want to have a good approximation of your PD. Okay, so here, so you have a semi-linear PD, and so now you know that you have a probabilistic representation for such semi-linear PD using all the theory of BSD. Okay, and so how it works? So you have this this linear part, okay, which correspond, okay, to a forward. Oh, why I have? Sorry, I don't know why it is. Oops. Okay. So you have some linear PDE, okay, which is associated to some forward diffusion, which here in this context correspond to the particle system of Martin-Vasov SD, or more precisely here because of the presence of a common noise of conditional or stochastic Martin-Vasov SD. And then, okay, you given this forward diffusion process, okay, you have a representation of your PD, okay, by means of a BSD. Okay, so in other words, so pair Yn Zn, okay, which is connected to so here HB is a nonlinear part, and so you have the connection with the PD through this Feynman-Macaque formula, so which says simply that Y, okay, is a solution to your PD evaluated at your forward process, and Z, the component Z, okay, it represents the gradient of the solution to your 5-dimensional PD, okay, evaluated at your forward process, forward particle system. Okay, and so now, okay, you have this BSD or probabilistic representation of your PD, and then you want to show, okay, that it indeed approximates where your the solution to your original PD, okay, so V, and so we define the so the error, the particle approximation error, so the error on V, okay, which is defined here. So it's the error on V, and the error on the L derivative. Okay, so here we take the L2 error, and so using, in fact, really a BSD arguments, BSD technique, which are more or less standard. Okay, we can prove, in fact, the following convergence rate. Okay, which says that okay, the convergence, okay, on V, okay, is of order 1/n, and moreover, so is this probably the main advantage of using a BSD technique. So we are also able, okay, to obtain, in fact, a conversion for the Z component. So in other words, for the gradient, okay, with L2 error convergence, okay, with an rate of order 1/2. Okay. So once you have, okay, now guarantees that your particle approximation converge to your original PD, okay?
Question? Can I? Yeah. Yes, please. In the error, could you go back one slide?
Yeah, sure.
The first error, you know, is that is there an expectation? Is
no, it's a pathwise error. So why it's almost sure error. So it's a pathwise error. For Y, we are able to prove a pathwise error. So we have of order 1/n with a constant, which is of course independent of omega.
So the constant is independent of omega?
Yes, of course. It's independent of omega.
Okay, cool. Thank you.
And but for Z, it's an error in L2. Okay, so now that we have reduced your problem to a 5-dimensional problem, so in principle we can apply, okay, the deep learning methods that have been designed for solving PD in 5 dimensions. So you can apply your favorite method, but still here the dimension, of course, is D multiplied by n, where n is the number of particles. Okay, and so typically the number of particles is 1,000, for example, and so the dimension is still very high. So it's not, of course, it's not very good to apply directly such method. And so in fact, the idea is to to exploit, in fact, the symmetry or the exchangeability property of the particle system to obtain both a better efficiency and accuracy. And for this, okay, we shall rely on a new type of networks, which has been specifically designed to deal with such kind of symmetry property, and which are called DeepSet. Okay, so to introduce what is DeepSet, okay, so let me first, give some, well, some basic simple definition about exchangeable function. So we say that a function is symmetric, okay, if in fact it is invariant per permutation of its input. Okay, so just symmetric. So it means really invariance, permutation invariance with respect to the input. The second definition, okay, is the notion of equivariance. And we say that a function, so now it's a vector value function, so it goes from xn, okay, to key n, yn, sorry, so it's a vector value. And so we say that it is equivariant if, in fact, it is both invariant permutation with respect to the input and output, which means that if you permute the input, okay, you permute similarly the output. Okay, so this is exactly the meaning of this relation. Okay, so example of symmetric function, of course, the max or the sum. And what we can show, which is not very, which is quite intuitive, but to prove it, we can prove it rigorously, is that, of course, the solution to your particle approximation, Vn, okay, is a symmetric. Okay, so it's invariant by permutation of input. Okay, so now we have also some important representation result on exchangeable function, which will be crucial to design suitable neural networks. Okay, and so which give, in fact, some a better understanding of a symmetric and equivariant function. Okay, and so the result is the following. I don't know why there is this red part. Sorry. Okay, so a function is a symmetric, okay, if and only if it is sum decomposable, okay, which means that it can be written, okay, as in this form, okay, so it's it involves two functions phi and psi, okay, and so you take psi of the sum of the phi of xi. Okay, so of course such function is symmetric, but the nice thing is that in fact it's any symmetric function can be written in this form. Okay, the second result is about equivalent function. So it says that an equivalent function, a function is equivalent if and only if, okay, it can be represented in terms of D-symmetric functions. What is a capital D-symmetric function? So it's a function with two arguments, so xn and x, and which is a symmetric with respect to the first n components. Okay, and so and then okay, the component of each of the equivalent function is equal to this D-symmetric function evaluated at the is component. Okay, so this gives you a representation of equivalent function. And the last property, okay, states that if you take the gradient of a symmetric function, which is differentiable, then it is equivalent. Okay, so such property, okay, has been recently proved. So the first one by Zahir, the second one by Boom and Reddy, and the last one by Maxime Germain, myself, and Xavier Varin. Okay, and so now based on this representation result on exchangeable functions, okay, so we can now build a symmetric function with neural network. Okay, and so the idea is simply to take for phi MC feed-forward network. Okay, and so then you get, in this case, okay, you obtain, when you take for S, the symmetric function, the sum, okay, you obtain precisely what we call the DeepSet. And if you take for the symmetric function S, the maximum, okay, you obtain as what is called the point net, which has been in fact introduced, I think, in parallel work in 17. Okay, and so of course, in view of this representation result, okay, we can prove that. So this author have proved the universal approximation for such a symmetric neural network. Okay, and so what about now equivariant neural network? So for equivariant neural network, so we rely on the representation result for equivariant function. And so there's two possible constructions. So either by using desymmetric neural networks, okay, so which lead to the what we call a deep DER set, okay, or because we know now that when you take the gradient of a symmetric function, it gives you equivalent function. So you can take the automatic differentiation of a deep set, and then you would obtain an equivariant neural network. Okay, so it's you have two possible ways to build equivalent neural network. Okay, and so now this slide is to show how the benefit of using such neural network compared to using classical feed-forward network, both in terms of accuracy and efficiency. Okay, so we test on 3 types of example. Okay, and so and we compare the number of iteration, okay, required to achieve a given level of precision. And for example, for the first example, okay, here, okay, you see that to achieve a level of precision 10 power minus 5, okay, with feed-forward you need almost 1,000 iterations, while for symmetric DeepSet, in fact, you only need 5 iterations. Okay, and the last example, okay, show you okay the benefit in terms of precision. So here we both use 1,000 iteration, but for the feed-forward we are only able to achieve this accuracy, while for DeepSet, okay, we are able to achieve this accuracy in the approximation of a symmetric function. Okay, and so now, okay, once you have this neural network, okay, you can apply the method, your favorite method to solve your semi-linear PD. So here we adopt the method that we have developed some years ago with Comuré and Zayvarin. So it is called a deep backward dynamic programming approach. Okay, so the generic algorithm is the following. So you have some PD, okay, semi-linear PD. Okay, so you know that it can be represented in terms of some backward SD, okay, with some forward SD, capital X here, okay, which related to the linear part of your PD. Okay, and so you have your BSD, you discretize, okay, starting from the terminal condition of your PD, and then you obtain naturally the following algorithm, okay, where you start at the initial time with a neural network equal to the terminal data, and then you proceed by backward induction. So at time k plus 1, you already compute your neural network, and then you minimize, okay, the loss function, okay, obtained from your discretization of your backward. Okay, and so you minimize both over y and z. Okay, so you estimate simultaneously, okay, both the value function and its gradient. Okay, and then, okay, you proceed by backward induction. Okay, and so you apply, okay, this method, okay, to the case of mean field. Okay, but now, okay, instead of using a classical neural network, so we use for the y component symmetric, a DeepSet network, while for z, which is equivariant, okay, we use a equivalent neural network, and more precisely, automatic differentiation of the DeepSet. Okay, and so we do several tests, but oops. Okay, and so here I simply I don't know why this red part. Okay, so here I simply take the very famous example now, okay, which mainly serve for many reference. So it's an example due to Carmona-Fook and Sun. So the main advantage, okay, so it has it comes from a financial problem. It has explicit solution. Okay, so it's a mean field control problem, and okay, and so because it has a solution, so we can compute the here as a result, okay, regarding the value function, okay, where we implement the algorithm with 10 runs of simulations. So we compute the average value, the standard deviation, and we vary both the number of time steps and the number of particles. And the last column reports, okay, the relative errors. Okay, and so you see that it gives quite good result using, okay, this DeepSet and AD DeepSet. Okay, another thing is that we also have, okay, an approximation not only of the value function but of the L derivative. So in this example, this linear quadratic example, the L derivative, okay, has this explicit form. Okay, so and then, okay, we compute the solution, the z component that we compare to the Lyon's derivative. So in orange, you have the z component, the Lyon's derivative, which is linear with respect to the x arguments. Okay, and in blue, okay, we report, okay, the solution obtained by the algorithm. So you see that it fits quite well the true solution. Okay, so now I think how much time have I left? Probably 10 minutes, okay?
Yeah, you have about 5 minutes, 5 to 10 minutes.
Yeah, okay. So for the second part of my talk, I would like to present some work, in fact, still work in progress. Okay, so related to solve some robust portfolio optimization by combining, okay, DeepSet, so that we already present, with DeepOnet. Okay, so let me start, okay, with the following simple problem. So it's just a Merton problem, or more precisely, a robust Merton problem with multiple assets. Okay, so it's a Black-Scholes model. So with constant volatility, constant drift or market price of risk, which is usually difficult to estimate. Okay, and so now we want to solve given some utility function. You want to maximize the expected utility from terminal wells. Okay, but because the drift is difficult to estimate, we want to compute not only for one lambda, okay, but by varying the parameter lambda. Okay, so in other words, what we want to learn, okay, is the map, okay, the mapping, okay, from the risk premium, the market price of risk, okay, to the solution to the Bellman equation for any lambda. Okay, so both for the value function and for the optimal feedback policy. Okay, so one observation is that, in fact, now if you look at this mapping, okay, it is a symmetric for the value function. So the value function is symmetric, okay, with respect to the lambda, while the feedback policy, the optimal control, is which is a vector in Rn, is equivariant with respect to lambda. Okay. This can be also extended to factor models in the sense that now if the market price of risk is no more constant but depend on the process, okay, y, which can be typically represented by factor of volatility. So now what we want to learn is now an operator, because we want to learn, okay, the mapping which map a function defined on this factor, okay, giving the solution, okay, to your optimization problem, and for the whole family of market price of risk coefficient. Okay, and the same for the feedback policy. Okay, and again, you can observe that you have a symmetry for the value function and equivariance for the feedback policy. Okay, and then another example, which maybe makes the connection with the first part of the talk, is Atlas type model. Okay, in stochastic portfolio theory. Okay, so now, so you have n stock. So it's in fact a rank-based model. Okay, which means that in fact the drift of the ith asset, okay, is determined by its rank among the whole asset. Okay, and so again, you can, for example, you may be interested in solving the portfolio optimization in this context, so investing in this log capitalization. Okay, and then again, okay, you do not want to solve only for one coefficient of the growth rate and volatility parameter, but for a whole range of parameters. So in other words, when now you vary, okay, the set of growth rate and volatility, so you have a family of value function and a family of optimal feedback policy. Okay, and what you can show, okay, is that you have some symmetry property in this Atlas model. In fact, you have joint symmetry property, which means that if you fix a lambda, okay, so the prime is symmetric with respect to the stock price x, okay, for the value function, and it is equivariant for the feedback policy. And on the other hand, now if you fix x, okay, and you view as a function of lambda, now both, in fact, the value function and the optimal feedback policy are symmetric, okay, with respect to this parameter lambda. And so now, in other words, what you want to approximate or to learn is this symmetric mapping, okay, so which maps lambda, okay, to v lambda, okay, to a functional space. Okay, so which means that more generally, what you are interested in, okay, is to learn symmetric operators. Okay, so in other words, you want to approximate a map, okay, defined from lambda power n, okay, which maps into another function, okay, where gamma here can be either a 5-dimension or a functional space. And it turns out that now we have okay, a very nice neural network which has been designed, in fact, to approximate operators, which is called DeepOnet. And so how it works, so its architecture is in fact divided, is decomposed into 3 parts. So first, an encoder. So what is an encoder? Is simply, so your input is a lambda, so it is a function. Okay, so you first encode by reduce the input to a 5-dimensional space. And otherwise, in fact, you will evaluate your function at some points, at m points, okay, called sensor points. Okay, and then you will use this 5-dimensional input of the function lambda, okay, you will use you will feed into another network called branch. Okay, so it's a network, okay, on the parameter lambda. On the other hand, since the output is a function of x, okay, you will use a neural network for x, which is called trunk network. You combine both network by a product, okay, and then you obtain, okay, you obtained, okay, the following DeepOnet, okay, which is just a product of the branch and the trunk. And so what we have is that we have a universal approximation for this DeepOnet, in the sense that, of course, if m goes to infinity, the number of branch goes to infinity, so it will approximate your operator. So in fact, it's all result due to Chen and Chen, which in fact the analog of the famous Hornick result. But in fact, what is more importantly, the nice result that we get is a very recent result, in fact, which appears just 1 month ago, okay, due to Lanthaler, Mishra, and Kanelakis, who proves that, in fact, such DeepOnet, in fact, do not suffer the curse of dimensionality, which means that, okay, the number of points m and the number of branch p that you need to use do not explode.
Huyen, okay. Just another minute or so. I think try to wrap it up.
Yes, okay, just 2 slides. And so now, if you have some symmetry in your problem, for example, if you have symmetry with respect to lambda, then the idea is just to use DeepSet for the branch. And on the other hand, if you have symmetry with respect to x, you can use a DeepSet or equivalent trunk, okay, depending if your problem is a symmetric or equivalent. Okay, and so my last slide, just to report some numerical, Okay, so just a numerical example, okay, which goes back to the first problem I presented. Okay, so the robustness problem. So now we want to learn, okay, the optimal control for a range of parameters. Okay, so using now a DeepOnet with equivalent branch, because the optimal feedback policy is equivalent. Okay, so now the training is a lambda. So you train lambda, okay, you train your wells using this DeepOnet feedback policy. Okay, and you apply just a global approach. So in other words, the stochastic gradient ascent method on your expected wells. Okay, and so the result that we obtain is reported here. So we take a quadratic utility function for which we have explicit result. And so in the table, okay, you have in the first column in the left, the optimal gain, the true optimal gain. In the second column, the training gain. In the third column, the validation gain, so where we use another test sample for lambda. And the last 2 columns is a control error. So the control error is the difference between the true control and the DeepNet. Okay, and you see, okay, both the training error and the validation error. Okay, so this is just preliminary result, but I think these are very promising. Okay, so because I'm already late, so let me just conclude. So as I try to show here, so there are many problems who possess, okay, symmetry feature. So in particular in finance, but in fact, not only and beyond finance. And from machine learning perspective, it's quite important to design a neural network architecture that fit well these problems. Fitting well means that there should be expressive, there should have some interpretability, there should be stable when training, they should generalize well, and they should they should break the curse of dimensionality, okay, in order to achieve an efficient and accurate resolution. And in that sense, okay, I believe that DeepSet and their derivatives, so the DeepSet and automatic differential DeepSet represent step in that direction. And moreover, when you combine with a DeepOnet, okay, or alternatively a Fourier neural network, okay, this allows you, in fact, to solve a variety of infinite dimensional problems. So, for example, a family of mean field type control problems. So, in other words, now you will be able to go from infinity to infinity. Okay, and so my last slide is just to to give some reference. So the first reference, okay, are related to the works that I presented here, and the last three ones, okay, it's the recent work about the DeepSet and DeepOnet neural network. Okay, so thank you for your attention. I think I will stop here.
Thank you, Huyen, for this very interesting presentation. I think we have a question from Tying Huyen. Please go ahead and ask. Okay, I think I will. Tai, are you there? Yeah, so I will ask you the question. He said that, if it would be possible to include consumption in the second part of your talk when you speak about robustness, and how does the optimal investment and consumption remain equi-invariant?
You mean in the first problem?
Yeah, in the second part of your talk, you mentioned.
Ah, okay.
I think when you speak.
Okay, you mean here a control part?
Yeah, when you discuss robustness.
Of course, you can add consumption. Yeah. In this case, the symmetry is still preserved.
Yeah.
And yes, of course, here I just there's no deal to include the consumption.
Yeah. Perfect. I think there is a question by Andrew Lyasoff. Andrew, please go ahead.
Thank you very much. Can you hear me now?
Yeah.
This is just a question in principle, maybe a bit naive. Is the approximation with delta functions, linear combination of delta functions, always the best, the most efficient one? What I'm thinking about is, what if we use parameterized family of distributions, like let's say gamma distributions, and are there experiments with that? Are there any theoretical results?
I'm not sure to understand well. So are you talking about the DeepOnet or for what?
No, for the general model. I mean, at the end of the day, we have to use, of course, we have to use a neural network, but we have a distribution. We somehow have to replace the distribution because the space of distributions is infinite dimensional, right? So we somehow have to reduce it to something that is finite. We have to put our hands on something finite. And so, of course, if we use delta functions in linear combination of delta functions, then those are dense. But what I'm asking is if there are experiments where we, let's say, instead of having delta functions, let's say we use gamma distributions, and then we have to run the neural network to learn, let's say, over just 2 parameters instead of n.
Okay, so you're talking about the first part. So
yes, the first part, exactly.
Yes, sir. So here, so I have not, I went very quickly. Of course, here, because in fact, you want to approximate your PD on the space of probability measures, which means that when you train your data, so the data should explore the space of probability measure. So it means that in practice, what we use is in fact a mixture of Gaussian law, because we know that a mixture of Gaussian law will, okay, at least will.
So you're using mixtures of Gaussian laws.
Yes.
I see.
But maybe there are other alternatives. But here, this is what we use.
This was not Somehow I missed that.
Yeah,
But
yeah, I go very quickly, but this is in particular what we use.
Yeah, thank you very much. Very interesting. Thank you.
Just last question before I give my closing remarks. Sebastian, please go ahead.
Sure. Hey, thanks, Huyen, for the interesting talk. I had a question about the DeepOnet. It's more, I guess, an intuition rationale for the particular choice. So you have branches and a trunk, right? And the branches take the inputs of the discrete form of lambdas in the particular application you were looking at, and then the trunk takes in the x values, and then you combine it with this sum product form.
Yes.
But I could imagine combining the branch and the trunk in a multitude of different ways, right? Not just sum products. I could take them as, flatten them, use them as inputs into another neural net layer, and then output the result. So is there some intuition or rationale for why this sum product form is what's used?
Well, so the intuition, I mean, there is a theoretical result, okay, which says that such form of when you take this product, okay, is dense in the set of operators. So this is actually the proof, okay, use this form of decomposition to get the universal approximation theorem. And also because for me it's quite natural to distinguish the lambda and the x components. And so it's so the fact to have parallel network,
Yeah, no, I get the intuition of separating them, but then combining them. The only question is, why is the
product?
I understand that, okay, there's a theorem that tells you that if you do this particular sum product, then you have a universal approximation for it. But I was wondering if there was an intuition as to why that seems to work so well, because it's in a way somewhat surprising, I guess, at least to me. Just wondering if there's any intuition.
I don't know if there's a really intuition about this. Of course, there are other methods because, as I say, there is now you have the Fourier neural network, which is a completely different architecture, which apparently seems to also works very well, and also do not suffer the curse of dimensionality. But maybe this one has the advantage of it's quite easy to implement. Right?
Mm-hmm. Indeed. Okay. All right. Thanks.
Yeah. Okay. Thank you. Okay, there will be another question for Julian, but you can ask him in the formal part. I just want to give some closing remarks. So today was the last seminar of this series. We will discuss what will be the future of this webinar series at the business meeting in our biannual meeting, which will be on June 1st. So we look forward to seeing all of you there, and of course, come to the meeting and express your thoughts and suggestions about what we should do going forward. I think at least I very much enjoyed it. I listened to a lot of very interesting talks and learned a lot from all the speakers and also participants. I hope it was the same for all of you, and just stay in touch and we will see each other at the conference. So we'll stop here with the recording, and there will be an informal part where